Part 2 is naming ionic compounds. So now we're going to talk about naming. We'll start with the ionic and then we'll move to the molecular and the acids. This is the big picture. I recommend while you go through this, this slideshow, have this handout, which you can find in the learning module in front of you. And it breaks it all down, and we're going to go through this piece by piece. The first part of it is the main breakdown, and it's important to recognize what type of compound you're dealing with: ionic, molecular, or acid. So how would you know? Look at the first element. If the first element is a metal, it starts with a metal, then you've got ionic. If they are all nonmetals, it's covalent. And if it starts with hydrogen, it's an acid. So the first thing you do in naming is identify that very first element: metal, ionic, nonmetal, molecular, and hydrogen is acid. So once we identify that it has a metal and we're in the ionic, the next part is to identify the cation and the anion. So the cation is the metal and it has the positive charge. The anion is the nonmetal and it has a negative charge. So looking at the cation, there are two types of cations. So the question is, does it have a fixed or a variable charge? And the next slide is going to be a periodic table, and hopefully this will make more sense there. But metals that have a fixed charge are mainly the representative metals. So it's the 1A, 2A, and 3A metals. And what it means by fixed is they're always the same charge. You don't have to wonder what charge is it going to be. You know it from the periodic table. And the ones with the variable charge are mainly the transition metals. And there's some exceptions to that as well. But the transition metals, tin and lead, have a variable charge. And what that means is in one compound it might be +2, another compound it might be +3. So you don't always know what the charge is based on the periodic table. And then notice there's these exceptions among the fixed. These are transition metals, but they always have the same charge. Let's see what this means on the periodic table. And actually, I think it's helpful to take a copy of the periodic table and color it. So the blue ones are going to be our fixed charge, and they are not going to need a Roman numeral. The yellow ones are going to be the variable charge, and we are going to give them a Roman numeral. So you can see that the representatives, the 1A are +1, the 2A are +2, the 3A are +3. Notice I didn't apply that to boron because boron's not a metal. The plus applies to metals. Okay? And so you know those columns, you know their charge. Then the exceptions from the transition metals: silver is always +1, zinc is +2, cadmium also +2. And I remember that making a diagonal with aluminum that's +3, we've got that 1, 2, 3 diagonal, and that's how I remember those charges. But if you'll color the transition metals yellow and the representative metals blue, and then here you see tin and lead, bismuth, even though they're representative, they have more than one possible charge. All right? And then when we name them, all you do is, so for example, calcium, that's going to become calcium ion. You just add the word ion because you know it's going to be +2 because of the column it's in. Now iron, that's one you don't know what charge it's going to be. So since it's 3, we're going to put a Roman numeral of 3 ion. So notice calcium's blue, it doesn't get a Roman numeral. Iron is yellow, we give it a Roman numeral. Because if I just said iron ion, you wouldn't know its charge. You can't tell from the periodic table. Okay, how about copper? Do we know its charge? Does it need a Roman numeral? Well, here it is. Copper, it's yellow, it does. So I'm going to put in Roman numeral 1 ion. Even though it's a 1, we don't leave it off this time. It's Roman numeral 1 because we need a Roman numeral. And then the last one, Ag, is silver. Does it need a Roman numeral? Well, let's look at it. It's transition, but it's blue. Silver is always going to be +1, so we just call it silver ion. So in naming the cations, if they're blue, they don't get a Roman numeral. If they're yellow, they do. And the Roman numeral is the charge. All right, let's look at considering naming the anion, okay? Again, we're going to have two categories of anions, but what they are this time, monoatomic, meaning it's just one element, or polyatomic, meaning it's a group of elements with a charge. So the monatomic are the nonmetals on the periodic table, and you can tell their charge from their column. The polyatomics are listed at the bottom of the table. They usually end in 8 or 8. You don't have to memorize these. You'll have them with you on the periodic table always, but it's helpful to be very familiar with these words, okay? So the monoatomics are going to end in "ide," and the polyatomics usually end in 8 or 8. So let's look at those a little more. Here's a list of the polyatomic ions. Notice one of them is positive. The ammonium ion is actually a cation, and so sometimes you'll see that instead of a metal in an ionic compound, but you just treat it like a metal, only it's a group. So that's the ammonium ion. You notice a lot of 8 and 8 endings. If you look at, say, nitrate versus nitrite, the difference is how many oxygens. So the 8 has more oxygens, the 8 has less oxygens. Everything else about them is the same. Notice 2 of them end in "ide." So we've got cyanide is one of them, and hydroxide. So it's kind of unfortunate. They end in "ide," but they're still polyatomic ions. And then these ones that start with hydrogen, they have 2 words. So hydrogen carbonate, hydrogen sulfate, that's one polyatomic ion. So when you hear those 2 words together, know to look for that one polyatomic ion. So now updating our periodic table a little bit more, I've colored the nonmetals green, and you can see their charge, -1, -2, -3, and -4. Now that -4 only applies to carbon and silicon, because then you get into the metals. The -4 is not super common. Carbon and silicon you find more often in molecular compounds. But when they're on ionic compounds, all of these, you'll change the ending to "ide." So we'll do some examples of that. And then I don't have it here, but in this corner here, you see the polyatomic ions. I colored them red. They end in 8 or 8. So this ending, "ide," 8, or 8, will give you a clue what you're dealing with. So let's see if we have some examples here. Let's try these examples. Determine the charge on the following nonmetals when they form anions, okay? And then name the anions. So F, when F forms an anion, what charge it's going to be? Well, F is here in the -1, so it's going to be F negative, and its name is going to be fluoride. It used to be fluorine, it goes to fluoride. All right, let's do the next one, S. Okay, S is right here. It's in the -2 column, so it's going to be S -2. That was sulfur. It's going to become sulfide, changing the ending to IDE. Let's look at P. P is in this column, so it's -3. And that was phosphorus. It becomes phosphide. IDE ending. And you may think, well, I thought that was phosphate. You may have heard of phosphate. That's a polyatomic ion. That has some oxygens on it. So it does have the P, but it's polyatomic. So watch for that ending. "Ide" means it's just the element. Okay, TE, you may not know the name of this one. TE is here, so you can see it's going to be -2. That's tellurium, so it's going to become telluride. I hope I spelled that right. And then the last one, C, that's carbon. It's in this column. So it's going to be -4, and that's going to be carbide. So change the ending to IDE. Ions don't exist alone. You'll never just have a sodium ion. It'll have to be with something negative. The charge always has to balance, okay? So if ions are the same and opposite charge, you can just put them together. For example, sodium and chloride. Okay, they have the same but opposite charges. They come together to form a neutral compound. The compound has to be neutral. Or if we have barium, that's +2, and sulfate, there's a polyatomic, it's -2, same and opposite charge, they come together to form barium sulfate. So it's very easy if they have the same but opposite charges. But if they don't, they can still form a compound. So for example, think about Fe with a +3 and OH with a -2. Okay, what that means that Fe needed to lose 3 electrons. But the hydroxide group only needed to gain 1. But imagine if you had 3 of those hydroxide groups, then they can each one gain 1, and so that's how we come up with the FeOH3. So it's called the cross the charge. So if we have Fe with the 3+ and OH with the minus, let's call it the -1, even though we don't usually write the 1, the charge on the 1 becomes the subscript on the other. So it becomes, I forgot my E, Fe, FeOH3. We don't need to write the 1. We need parentheses, otherwise it looks like only the H got the 3 subscript. The whole group got the 3, okay? So anytime you have a polyatomic ion and a subscript, it needs the parentheses around it. So let's try some of these examples. So we have NH4 and PO43. Do they have the same charge? They don't, okay? So we're going to cross it. So the NH4 goes in parentheses and gets a 3 subscript, and the PO4 doesn't need parentheses because it's getting the 1. All right, the next one, SN +4, and C2O4 2-, do they have the same charge? Nope. So let's cross them. So we do SN is going to get the 2, C2O4, the oxalate, is going to get a 4. Just crossing the charge. The 2 goes down here, the 4 goes down here. But this one's a little tricky, because this 2/4 is not the simplest ratio. You wouldn't write a fraction of 2/4, would you? You'd say, no, that's 1/2. Simpler. So we can simplify this as well, okay? And we'll write it SN C2O4 2, simplifying that. And the last one, I'm kind of running out of space. We have CR +3, P -3. Are those the same? Yes. This time they are. So this one is just CRP. And that's how we write the compound. So the important thing is that the charge has to balance, that we have to have the same amount of negative and positive, and we can get that by crossing the charge if it's different. So now that we know how to make the compound, let's talk about how to name it. All you do is name the ions. So consider our favorite and simple one, Na and Cl. They have the same and opposite charge. We put them together, NaCl. All right, that's the formula. For the name, this Na+ is called sodium ion. Cl-, remember, chloride ion. Change the ending to I. And now to make the compound, you just drop the word ion, and it becomes sodium chloride. That's the name of that compound. That sounds very familiar because you know that compound, but it's the same rule that applies to all of the ionic compounds. Let's look at another one. Here we have Ba2+, SO4 2-. Same and opposite charge, so you just put them together, BaSO4. Then we look at the names. This one's called barium ion. This one's called sulfate ion, 8 from the polyatomic ions, okay? The compound, just drop the word ion, and you have barium sulfate. This next example, we have Fe3 plus, OH minus, okay? Those are not the same subscripts, so we have to cross them. So we get FeOH3, and that's the formula. Then we come to the name. Remember, Fe needs a Roman numeral, so its name is iron 3 ion. Because it's yellow, it needs the Roman numeral, and I kept the same color coding here. Hopefully that helps you see them from your colored periodic table. OH minus from your polyatomic ions, that's called hydroxide ion. And then when you get to the name of the compound, you drop the words ion, and you have iron 3 hydroxide. Okay? It's important to keep the 3. You need the Roman numeral because you don't know iron's charge without that. But the thing that's tricky about this is that this 3 is not the subscript on iron. So iron has one subscript, but its charge is 3. So notice that 3 is the charge, not the subscript. So remember that. Go back to the ion, see what its charge is, and that's the Roman numeral. So let's try some examples. And what I really recommend is that you pause it here and try these on your own, and then turn it back on and check your work. So the first column, we have formulas, and we're going to come up with names. The second column, we have names, and we're going to come up with formulas. So let's go ahead and do these. Here we have NH4, okay? And let's start by just naming that. That's a polyatomic, and that's called ammonium. And you know that just by looking at your polyatomic list. And then the next piece is also a polyatomic ion, and that's called phosphate. So this compound is ammonium phosphate. The subscript is not part of the name. Don't worry about that. We don't need that in the name. Next one, we start with the metal, Sn. Hopefully you remember that is tin. And then you always ask yourself, does it need a Roman numeral? Well, and you look at your periodic table, it's yellow. Tin does need a Roman numeral. I don't know what it is, but I'm going to make the parentheses for my Roman numeral and come back to it. And I'm going to figure out what the charge on the tin is. Remember, the Roman numeral is not the subscript, it's the charge. I'm going to figure that out from the anion. So now I look at my anion, and again, it's polyatomic, so I look at my list, and that's called oxalate. So that's its name. The other thing I identify is its charge. Its charge is 2 minus. And from that, I can figure out what the charge on tin is. Because if this is 2 minus, and I have 2 of them, I have a total of -4. So I've got to have +4 as well. So +4, that's my Roman numeral. The tin has a charge of +4. So the name is tin 4 oxalate. 4 is the charge, not the subscript on the tin. All right, next one, Cr, that's chromium. Does it need a Roman numeral? It's transition, yes. So I'm going to leave a space for my Roman numeral and come back to it. This piece, P, it's not polyatomic, so it's going to be an ide. And it's phosphorus, so it's going to be phosphide. Okay, also notice its charge. It's in the column that's -3. So if the P's got to be -3, they've got no subscripts, so the Cr has got to be +3. So my Roman numeral is 3. Chromium 3 phosphide. Let's look at the other style where we know the name and we're trying to get to the formula. So the first one, calcium. Calcium is Ca. So what I'm going to do is I'm going to list the ions and their charge, and then I'm going to put it together in a formula. So calcium's charge, you know from the periodic table, 2+. Okay, permanganate, 8. It tells you it's polyatomic. Look at your list of polyatomic ions. You find that it's MnO4, and the charge is minus. Okay, they don't have the same charge, so use your cross rule, and it's going to be Ca parentheses MnO4 parentheses 2, cross the charge, and there's your formula. Now we have lead to chromate. Lead is Pb. Now it's yellow, you might not know its charge, but since you have the name in the Roman numeral, you know its charge. It's 2. Lead 2 plus. And chromate, again, 8, it's polyatomic, CrO4 minus. Okay? They have different charges, so we're going to call it Pb parentheses CrO4 parentheses. Wait, chromate is minus 2. So in this case, we don't need parentheses. It's just Pb CrO4. Sorry, I don't have my list in front of me, and I got that. Remembered that wrong. So they have the same and opposite charge, so you don't need a subscript, you don't need parentheses. And then the last one, nickel 3 hydrogen carbonate. Okay, nickel 3, Ni with a plus 3, so the Roman numeral tells you. Hydrogen carbonate, it ends in 8. Look at your polyatomics. The hydrogen carbonate is HCO3 minus. They have different charges, so cross them. It's going to be Ni parentheses HCO3 parentheses 3, and that's your formula. So this slide just has everything written a little more cleanly and same information as the last slide.